What is the real basis for lattice classification? The answer is symmetry. And to justify this claim, we have to understand the concept of symmetry first. An object is said to be symmetric with respect to a particular geometric operation if it can be brought into the self-coincidence after performing that geometric operation. To understand this abstractive definition, let's take an example which will give us the concrete understanding of concept of a symmetry.
Here I have taken two square lattices. All the lattice points of one lattice are shown in green color, while these are highlighted in red color for the second lattice. In the green lattice, I have marked a lattice translation by a green vector along the horizontal direction. And now I am going to perform a geometric operation on these lattices to check whether these two lattices are capable of attaining the coincidence with one another. While performing this geometric operation, I am going to shift entire red lattice over the green lattice along the green vector. Here I have started sliding my red lattice over the green one. While doing this geometric operation, I have witnessed that given lattice do not coincide with one another until and unless the shift is equal to the lattice translation. All the lattice points of the red lattice occupies the exact position as that of the green lattice points when the shift is equal to the green vector. Thus, this shift, that is, the shift by lattice translation vector, is a symmetry operation of this given lattice, and we call it as a translation symmetry. Green lattice contains many lattice translations. So, we have to check the capability of these two lattices to attain the coincidence with one another along rest of the lattice translations. Now, I am going to slide red lattice along the vertical blue vector. When I do so, red lattice once again come into the coincidence with the green lattice when the shift is equal to the vertical lattice translation. Now, let's check this coincidence between green and red lattice along the diagonal vector, which is shown in black color. If I go along the black lattice translation, I again witness the coincidence between green and red lattice.
So the given lattice is self-coincident with respect to many different lattice translations, and all of them are symmetry operations. Thus, we can define lattice as a set of points possessing translation symmetry. Thus, translation symmetry becomes the defining symmetry of that lattice. In addition to this translation symmetry, lattice may possess non-translation symmetry as well. This non-translation symmetry, also called as point symmetry, because in case of translation symmetry, all the points get shifted, but few points remain unchanged in case of point symmetry. To understand the concept of point symmetry, let's look at few examples.
Let us look at some examples of point symmetry operations. One of the most important point symmetry operation is the rotation about an axis by some angle. If this rotational symmetry operation is capable of bringing the given lattice into the self-coincidence, then that particular lattice possesses rotational symmetry. But in this operation, all the lattice points get shifted except the points which are present onto the axis of rotation. Reflection in a mirror plane is another point symmetry. Here we are going to have a mirror plane and a lattice on the one side of this mirror plane. This lattice will be imaged at an equal distance on the other side of the mirror plane. In this operation, all the lattice points move to the other side of the mirror plane, but the points which are present on this mirror plane will remain invariant. One more point symmetry we have is inversion. In this case, we have a center of inversion. Our lattice will be placed at a distance x from this inversion center. All the lattice points will get imaged on the other side of the center of inversion by exactly equal distance. But the points which are present at the inversion center will remain invariant. Let's look at the details of rotational symmetry first. An object is said to possess an n-fold axis of rotation if it is brought into self-coincidence by rotation through a minimum angle of 360 degree divided by n. For example, if we have n equals to 1, then theta mean will be 360 degree. Any object which is having regular or irregular shape will always come into self-coincidence if it is rotated by 360 degree. We can call this as a one-fold symmetry or no symmetry. When we take n equals to 2, then theta mean will be 180 degree. So the object will have two-fold symmetry or two-fold rotation axis. For example, shape of capital N. If we rotate capital N about the given central point by 180 degree, capital N comes into self-coincidence. But this self-coincidence of capital N will not be witnessed if it is rotated by 90 degree or 270 degree. Thus, capital N possesses two-fold symmetry. If we will check the same concept for other letters like capital A, we will not witness any self-coincidence for capital A about two-fold rotation axis. Now, let's apply this concept of rotational symmetry to the two-dimensional geometries like rectangle, equilateral triangle and polygons. First, I have taken a rectangle. This rectangle will come into self-coincidence when it will be rotated through 180 degree. Thus, a rectangle possesses two-fold rotation symmetry. This two-fold rotation symmetry axis passes through the center of rectangle along horizontal and vertical direction. Next, we are going to look at an equilateral triangle. This equilateral triangle will come into self-coincidence by 120 degree rotation. Thus, it possesses three-fold axis of rotation. Next, we have a square. A square can be brought into self-coincidence by 90 degree rotation. So, square possesses four-fold symmetry axis. In our list, next we have a pentagon. Pentagon attains a self-coincidence when rotated through 72 degree. Thus, pentagon has five-fold symmetry. Finally, I am going to take hexagon. This hexagon possesses six-fold symmetry because it comes into self-coincidence after rotating through 60 degree.
From this illustration, we can conclude that in case of any regular polygon, n-fold symmetry depends upon number of sides of that particular polygon. So, we can find out object of any symmetry. But when we want the symmetry to be present in any crystal, that crystal must possess rotation axis of n-fold symmetry for n is equals to 1, 2, 3, 4 and 6. It means until and unless the rotational symmetry is not compatible with translation symmetry, we cannot represent that object as a crystal or lattice. And this is called as crystallographic restriction theorem. According to this theorem, only one-fold, two-fold, three-fold, four-fold and six-fold rotational symmetry is compatible with translation symmetry. I will end this discussion here and further discussion I will continue in my next video.